So there are systems in the brain that are interested in the signals that come from the heart with each heartbeat. And we've been looking at these baroreceptor afferent effects. So this shows a cardiac cycle. So this is the ejection of blood out of the ventricles. It's this period here. During this period here, baroreceptors, which are stretch receptors in the aortic arch and the carotid sinuses, they fire due to the distension of the vessel by blood being ejected out of the left ventricle. And that signal actually drives the baroreflex whereby blood pressure is controlled. But we've been showing that we can present brief stimuli at different phases of the cardiac cycle, either when these baroreceptors are active at cardiac systole or before that at diastole, late diastole or pre-systole, and show differential effects of the heart signal on the processing of stimuli. So this shows a fear face. When you see a fear face at cardiac systole, you rate that face to be more fearful than when you see it at diastole, and to some extent the opposite, or there's no effect for other types of faces, in this case neutral. So this is really what I'm going to be talking about for the rest of the talk, with some digression now. Oliver Cameron mentioned the ancient Greeks had an idea about interoception. The Hippocratic doctors, they were true medics, experimentalists, dissectors. They argued that the source of pleasure, merriment, laughter, amusement, grief, pain, anxiety, tears is the brain, and that the diaphragm nor heart neither take part in mental operations. And they derived that view from experiments in animals and observations in wounded soldiers and so forth. But following that, Aristotle argued quite the opposite. He said the brain is not responsible for any of the sensations. The correct view is the seat and source of sensation is the region of the heart. The motions of pleasure and pain, and generally all sensation, have their source in the heart. And Aristotle was quite influential in the development of the medieval church and thinking around that for some time. These two views seem quite incompatible, but I guess, you could argue that there may be something you could say that maybe the motions of pleasure, the emotional responses, originate in the body, and the actual processing of it in the brain can find some compromise between them. And people have thought about it over the years with models like the James Lang model, reviving the notion of peripheral influences on emotion. I see interoception as the opposite of exteroception. I see exteroception as seeing, hearing, tasting, smelling, touching, those kind of proprioception, information about the world outside you. Interoception, likewise, is a collection of channels, a collection of senses about the inner state of the body. These include mechanical sensations and information about the state of distension of bodily organs or their movement. Chemosensory information, which includes things like blood gases, pH, nutrient sampling, hormonal, humoral, endocrine, immune responses, and signals of tissue damage, and other processes like core temperature. Again, I go by the notion that Sherrington proposed that there are interoceptors in the body that are the source of interoceptive information. I see interoceptive information as being the core feature of interoception. Interoception signals the normal and abnormal functioning and integrity of the body, and is the afferent limb for homeostatic reflexes and allostasis. Okay. I don't believe that you need to perceive these sensations to call this interoception, Perception is an evaluative process that goes on top of the interoceptive signaling. Conscious access to those signals may or may not be present. Interoception includes these aspects, but is not necessarily defined by them. I mentioned that I don't think smell and taste, where you sample the environment even if you're about to swallow it, I don't see them as interoceptive senses. Proprioception and balance, body position in space, I don't see that as interoception, although many philosophers seem to argue proprioception to be similar. The skin temperature, accessible mucous membranes, stimulation of those I don't really see as interoception, although obviously they share same or similar pathways. There are a number of studies on interoception that look at electrodermal activity, and I do worry about these because I don't know of an afferent feedback loop from skin conductance responses. You could argue that maybe temperature from sweating, but if you're just measuring this physiological signature of central arousal, for it to be interoceptive, there seems to be a missing link there, the afferent information from the periphery. There obviously a need to integrate and represent in a more holistic way the information from the body, but I'm quite keen that interoceptive experiments first start off with the basic channels and look at the integration and the representation. Rhythms of the body are second-order representations, as are things like emotional feeling states derived from accessing the signal and representing that signal in a conscious or perceptual way. Same goes for processes that direct attention to the body. Unless there's an afferent feedback from the body, it's difficult to argue that just focusing on different sensory channels is interoception. It's a directed attention task. Okay, so feedback from the body will come up the spinal cord, up the cranial nerves. We can say something about the central mechanisms through which these signals are relayed and processed and feed back to control systems that alter body states appropriately or predict the need to change body states. I'm going to talk about, go back to cardiac interoception. When I went to Queen's Square, I started working with an autonomic unit where I had access to patients that provided quite interesting lesion deficit models for studying autonomic processing. And among them were people with a peripheral autonomic neuropathy that was acquired in middle age, who couldn't generate changes in heart rate, blood pressure, skin conductance because of an autonomic denervation that's affected both sympathetic and parasympathetic systems. They provided a model for impoverished interoceptive feedback, although in principle their interoceptive pathways were intact. What was missing was the actual response that would be signaled up via interoceptive pathways. So I'm going to talk about them. I'm going to talk about studies using fear conditioning and heartbeat detection, and more about the brain and the heartbeat signals that I introduced at the start, and heartbeat timing experiments. Yeah. So in fear conditioning, if you give someone an aversive event, it will generate an autonomic response. If you pair that aversive event, whether it be a loud noise or an electric shock, if you pair it with a previously relatively innocuous stimulus, this stimulus comes to predict the aversive event, and in itself will generate the body response, including an autonomic component to that response. And stimuli that have never been paired with the shock or the loud noise will be safe stimuli and not generate the same magnitude of autonomic interoceptive change. We can play around with people's awareness of the threat stimulus using backward masking. If we show a conditioned stimulus quickly and replace it rapidly with a masking stimulus, we can show that the autonomic changes can be induced without people being able to access a conscious recollection of having seen the threat. So we can show that autonomic responses are automatically generated by threat in the absence almost of conscious perception. So this is the experiment that I did in patients with pure autonomic failure, fear conditioning experiments, where we conditioned a face with a loud noise in this case. We looked at healthy controls and patients with this autonomic denervation. Both groups produced a motoric response that showed the learning of threat, but the patients didn't have the autonomic component of this response that normally is present in healthy controls. Both the controls and pure autonomic failure patients learnt the association between the loud noise and the threat, and that learning took place in amygdala among other regions, but mainly confirming that conditioning had occurred. There were differences, though. In the absence of an autonomic response, there was a reduced activation of right insular cortex and other regions of amygdala, suggesting that threat processing, but without the autonomic component, or without the feedback of the autonomic component, was greater. So it was diminished. The activation of insula and amygdala was sensitive to the presence and absence of this autonomic change that occurred in the controls and not in the patients. And in this experiment, we played around with the awareness of the threat stimulus. If we present it after a neutral face, people see the threat. If we present it before, in a masking paradigm, the people being scanned can't see the face. And the patients don't generate the autonomic arousal component of the response to the threat. And doing this, we showed that regions of right insular cortex were interested not only in the presence and absence of body response, autonomic body response, but were also interested in the conscious awareness of the threat itself. And we interpreted this in terms of Schachter and Singer's two-stage model of emotion, whereby a physiological response signals the onset of an emotion and intensifies the feeling of that emotion, but the actual additional component needed is a conscious representation or a cognitive representation of what the cause of that physiological change was. So we're saying that the conjunction of a physiological change with a conscious perception of an emotive event occurs in right insular cortical regions. So that study really suggested that there are areas that are interested in interoceptive change in the context of an emotional challenge. At the same kind of time, Stefan Wiens, Arne Oman, Ed Katkin published a paper, maybe the year before, where they conditioned one of two stimuli to an electric shock, so it generated a body change. But they presented the shock after a delay rather than at the same time as the stimulus, and this is called the trace conditioning paradigm. And trace conditioning paradigms kind of require people to hold a representation of the stimulus over the course of a period where the stimulus isn't presented in order to make the association with the shock, and it's been used as an animal model of conscious retention of information. So what the group did was actually present the stimuli subliminally, backward masking both the CS plus and the CS minus, the threat and the safe stimulus, and asked people whether or not they were going to get the shock. And in theory, because they can't see the stimulus, they should be unable to predict whether they were going to get the shock or not. And they found that some people could do this task, and these people that could do the task were good at a heartbeat detection task. So they were interoceptively more sensitive or more accurate in performance of this task, the Katkin-Whitehead type of interoceptive task, which I'll come to in a second. So the idea here is that in the absence of a conscious perception of the threat, these people could read out their body state and predict whether they were going to get a shock. And only the people, though, that could read out their body states And the task itself was presenting a series of musical notes, either in time with the heartbeat or out of sync with the heartbeat, or, sorry, delayed by a fixed interval. And people had to discriminate between those two types of presentation. It's a relatively difficult task, but it allows to differentiate people that can do the task from people that can't. The argument was that people that are good at perceiving changes in their internal body state are good at this task, and they experience things like emotions with greater intensity by virtue of being more attuned to the emotion-induced changes in their body. And Stefan Wiens and Ed Catkin had shown this for people's judgment of films, whether it be happy, amusing, angry, or fearful films. And more generally, the concept of interoceptive ability that had been around was reinforced by that kind of data. The idea being that there are individual differences in the strength of the channel from the body to the brain. And one can access or determine good and bad interoceptive ability by tasks such as whether people at rest can feel their heartbeat beating or not. And it's a test, these kind of tests are tests of individual differences, not within subject changes. So the idea is that the interoceptive ability is fixed for people, it's rather unchangeable. Obviously, when you run, you can feel your heartbeat, but we're talking about a low-level rest condition and how sensitive people are to their body, to their heart beating. And people that are more sensitive, perhaps are more prone to anxiety disorders, as some data may experience more intense emotions, may be more sensitive to pain, but on the positive side, may be able to use this information in positive ways, like making intuitive decisions, may be more empathic to other people, and better able to regulate their own emotions or even their sense of selfhood. And so there are two types of tasks, and I know this is familiar to most people, but the Chandri counting task gets people to start counting silently over fixed intervals, and during the process of sitting still and counting how many heartbeats are felt, an EKG is measuring people's actual heartbeats, and the reported heartbeats is compared to the actual number of measured heartbeats, and that gives an index of heartbeat tracking or heartbeat counting accuracy. The heartbeat discrimination task, I said, people hear a musical note or see a flashing light that's either in time with the heartbeat or out of phase. And people have to discriminate between runs of these notes to get an index of whether or not they're able to discriminate their heartbeat with any accuracy. So within our group, Sarah Garfinkel has, in my view, produced the kind of step change in this type of study by defining not only these performance on these tasks as kind of an objective measure of behavioural interoceptive accuracy, but also comparing that to people's beliefs and subjective ratings of their interoceptive abilities, so confidence ratings during these tasks or questionnaire ratings of how many or how sensitive they are to internal bodily sensations would form this subjective measure of sensibility. And then the two can be compared to give an index of awareness, so metacognitive accuracy. So you can be aware that you're a bad heartbeat detector or aware that you're a good heartbeat detector. And as has been said previously, that's interesting because where people's subjective and objective reports of performance on these tests, their subjective ratings and objective performance diverge, we start getting symptoms, in this case in the autism group, in blue, and healthy controls in the same experiment in yellow. We get increasing trait anxiety with increasing interoceptive trait prediction error. So the mismatch between these axes of interoception. So that's a bit of a digression as well. We used a heartbeat we used this heartbeat discrimination task in an experiment that was widely cited in 2004. So neuroimaging experiments where we had the heart condition where people did this Kapkin-Whitehead task to get a measure of how accurate they were at interoceptive cardiac detection. We had a note condition where they had to detect as a control whether or not there's a slight change in one of the notes in the sequence, and that's an exteroceptive control condition. And actually, comparing the two gave our measure of interoceptive sensitivity in a noisy scanning environment. So we actually got a spread of people during the task. And the main finding that's often reported is that the right anterior insula provided the best correlate of people's performance on this interoceptive task, their interoceptive accuracy. And we showed that that also predicted day-to-day symptoms of anxiety, and the insular response predicted anxiety, as did the interoceptive sensitivity accuracy score. That experiment had a lot more data in it, in fact. So we looked at just focusing on your heartbeats compared to focusing on these exteroceptive changes, the note trials. And when people just shifted their attention internally, we saw activation of bilateral insular cortex, somatomotor cortex, supplementary motor area, anterior cingulate. All these areas show increased activity when people were focusing on their heart relative to just the quality of the notes they heard. There are other areas that were interested in the presence and absence of delays between the external notes and their own heartbeat as a function of their attention. So this is the areas that are more active when there's a delay between your heartbeat and the note, compared to when there's no delay, compared to when you're focusing on the note itself. And some areas, like the right anterior insular opercular region, did both. So that showed a main effect of attention, showed the interest in the synchronicity of an external and internal stimulus, and also predicted interoceptive accuracy. So these data showed that the insula and amygdala were both interested in interoceptive signals from the heart. But the insula in particular the activity there interacted with the processing of external stimuli. The activation and the cause of the activation being physiology seemed to be translatable into a reportable experience of sensing your heartbeat, and correlated with predictors of anxiety, reinforcing the idea that emotional feeling states have an origin in physiological changes within the body, mediated through regions like insular cortex. And we noticed that this region was interested in relative timing between external and internal stimuli. So I'm going to return to this heartbeat timing paradigm. So every time the heart beats, baroreceptors fire off in the aortic arch, carotid sinuses, systole. A strong heartbeat in terms of gives a big distension, a big signal from these baroreceptors. This is transmitted into the medulla and through a reflex mechanism called the baroreflex. You get a slowing of the next heartbeats mediated through the vagus influencing the sinoatrial node of the heart. And you also get an vasodilatation in muscle vascular beds through an inhibition of muscle sympathetic nerve fibers. So a strong heartbeat, a beat and a bit later will cause a drop in blood pressure. The interesting thing about the cardiac cycle, these phasic systolic baroreceptors signal the timing and strength of individual heartbeats, therefore is really the main signal for cardiovascular arousal. It's also the basis of the baroreflex and, by extension, of measures of heart rate variability. So we can use the impacts of this cardiac the phasic nature of this cardiac signal to explore how this channel of information influences processing of external stimuli or emotional challenges, provided we present those external stimuli or emotional challenges very briefly at systole and compare it to diastole, because at systole you get the baroreceptors firing to the brain, and at diastole you don't. So we can examine the effects of the cardiac afferent arousal channel without having the person in a state of arousal with all the cognitive and other confounds of being aware that you're more aroused. The reason why we got into this was actually because of Gunnar Wallin, who's a microneurographer from Sweden. He'd been doing studies measuring muscle sympathetic nerve traffic. So this is a burst of a bundle of sympathetic nerves supplying the muscle vascular beds. And they burst because of this baroreflex mechanism. They're inhibited with each heartbeat. It's a slight latency in the inhibition. And what they were showing was if you present electrical stimulation at cardiac systole, you get an inhibition of muscle sympathetic nerve traffic. You get no effects on other measures of sympathetic nerve firing, like skin sympathetics. So electrodermal responses don't do this. But the conjunction of electrical stimulation at systole causes a conjunction of electrical stimulation with systole, with baroreceptor firing, causes an inhibition of muscle sympathetic nerves. And that kind of inhibition habituates quite quickly. If you present a sequence of pulses at cardiac systole, you only really get one inhibition if you're healthy. But if you suffer from blood phobia, needle phobia, and you present a sequence of these stimuli at systole, you don't get the inhibition. You don't get the habituation of the inhibition. So there's a difference between people that faint at the sight of needles and blood and people that don't. It's quite basic interoceptive versus electrical stimulation level. So there's processes going on whereby the internal body state determines whether or not a stimulus that's externally delivered to someone is perceived in a particular way or reacted to autonomically. And the focus had been not really on pain stimulation because, high blood pressure and signals at cardiac systole inhibit the processing of pain. So if you present painful shocks at cardiac systole at the time of baroreceptor activation, you get a decrease in perceived pain. You get a decreased pain ERP, electrocortical potential. And you get an attenuation of nociceptive reflexes. Other groups have shown that if you can augment these effects by applying neck suction at the time of cardiac systole. So again, you get this augmented inhibition of pain reflexes, perceived pain, and cortical potentials to pain. So we did, in collaboration with Gunnar Wallin, a study in an MRI setting. So this is Marcus Gray, 2009, got published. We were measuring beat-to-beat blood pressures, skin conductance, pulse oximetry, which was actually our main trigger for the pain stimuli on and off systole. But we measured ECG in order to validate our predictions based on the pulse. What we showed was that a painful shock stimulus given at diastole produced an increase in blood pressure. If you gave that shock at systole, you got an inhibition of that blood pressure response. And that occurred for both diastolic and systolic blood pressure. And within the brain, the areas that seem to mediate this effect of shock, giving a shock at the time of baroreceptor discharge were dorsal brainstem regions, which inhibited at the time of cardiac systole, bilateral insular cortex doing the same, and the opposite effect in amygdala. So cardiac systole and concurrent with a pain stimulus caused an enhanced activation of amygdala. Usually I only present that one slide, but it's interesting to look at individual differences in this effect. So people vary in their parasympathetic cardiac tone as measured by heart rate variability, and this shows the heart rate variability spectrum. So high frequency heart rate variability is seen as being predominantly parasympathetic. If it's large, you've got more parasympathetic tone, more respiratory sinus arrhythmia, and it's arguably an indicator of good health. Well, so people with, this shows that individual, in fact. So people with greater resting parasympathetic tone show an enhanced response in amygdala compared to people with low cardiac sympathetic tone, parasympathetic tone, sorry. And also regions such as, regions such as amygdala and periaqueductal grey also predict whether or not you're going to get a parasympathetic response following the shock or not. So these brain areas are linked to both parasympathetic control and the conjunction of afferent interoceptive cardiac signals. So the processing of salient external stimuli, in this case electric shocks, is gated as a function of these interoceptive cardiac afferent signals. And the brain region involved, including the suppression of pain responses and autonomic responses to pain. We've got the insular dorsal brainstem are inhibited, amygdala activity is increased. It's a relationship between the engagement of these areas and resting parasympathetic tone and in parasympathetic reactivity following stimulation. So that shows, this shows an impact of interoceptive signaling on pain processing modified by individual differences in physiology. Because we've shown this effect, we got interested in what else these phasic cardiac signals could do. And obviously, there's lots of models of fear conditioning as a model for anxiety and PTSD and so forth. And we wondered whether we could change the value of stimuli that were potentially threatening to an individual with an anxiety disorder by capitalizing on these cardiac timing effects. Simple first experiment I've shown was to present different emotional stimuli at diastole or at systole. And we showed that the impact of the intensity ratings of facial expressions of fear was greater at cardiac systole compared to diastole, of a magnitude much more than we saw for other emotions. And for neutral faces, there may have been a slight change, but in the opposite direction. So this enhancement of fear processing at cardiac systole is the opposite to what we saw with pain. We saw an inhibition of pain at systole. Here we're seeing enhanced threat processing at systole. In the brain region among the brain regions that reflected this or mediated this effect was the amygdala, showing an increase in fear responses at cardiac systole. So Sarah Garfinkel's work in 2014. What was interesting about this activation was that it predicted within a relatively normative student sample the expression of anxiety symptoms. So the more you had this systolic enhancement of threat and engagement of the amygdala associated with it, the greater reported anxiety symptoms in this relatively healthy population. We used the emotional attentional blink paradigm as another way to look at how heartbeat signals might affect the processing of fear, external threat. In this case, the emotional attentional blink paradigm, you present a rapid sequence. This is like 750 millisecond sequence of 15 images, or most of which are jumbled masks. But there are two targets. There's a house and there's a face in the sequence, and you have to detect both targets. If you detect the house, you generally miss the face, and this is called an attentional blink. But if the face is strongly emotional, it can break through the attentional blink. So we were interested in manipulating the timing of this second stimulus as a function of systole and diastole to see whether that affected the breakthrough and therefore the emotional intensity of this threat face, fear face. And what we found was, relative to other emotions, the only emotion that showed an effect of cardiac timing was for fear. So fear faces were better detected at cardiac systole than at diastole. And for the other emotions, there wasn't an effect with a slight change for neutral faces in the opposite direction. So this was quite a strong effect indeed. You know, the heart signals were enhancing the detection of threat. It means that if your heart's beating strong and fast, you're more attuned to threat in your environments, but less attuned to other emotions. It wasn't shown by everyone, so 5 people, 3 didn't show any effects, and a couple showed a slightly opposite effect. And it got us interested in whether this could be interesting to explore in patient groups with anxiety disorders, whether these individual differences told us something about the expression of anxiety. So fear processing at systole is enhanced, fear detection is enhanced at systole, fear faces are rated more salient at systole. There's no effect really on other emotions. With the ratings, we saw a slight change we discussed in one experiment, but not in the subsequent experiments. And the individual differences are interesting. We've extended this paradigm actually using something equivalent to a binocular rivalry experiment. Here we present an image to each eye separately. One of the, either a neutral face or a fearful face. And the idea is if you see a different image presented to different eyes, you really only perceive one of those images. And we can titrate the degree of contrast in the fearful face to get a measure of the perceptual threshold of the emotion of fear, because more emotionally salient stimuli would be seen over neutral stimuli in this binocular rivalry experiment. So people were presented with 2 stimuli. One was a neutral face, one was a fearful face. We had a stepwise modulation of the contrast of this face to get a threshold for detection of fear. And we presented these pairs at diastole and at systole. So only one face is perceived. What we saw was that people with high interoceptive accuracy, that's good heartbeat detection accuracy, detected fearful faces better at cardiac systole in this paradigm. So it reinforces our observation, but also links it back to individual differences in heartbeat detection tasks. So we've seen physiological modulation, individual differences in physiological tone, heart rate variability, as a modulating influence on the effects of heart, interoceptive cardiac signals on pain. Seeing anxiety modulating the effects of brain responses to the conjunction of fear processing and the heart signals. And here we're seeing heartbeat detection accuracy, partially modulating the effects of heart signals on fear detection. So we've been pursuing this paradigm in different ways, not just with face stimuli, different types of threat stimuli. We wondered whether we could change people's perception of phobic stimuli as a sort of work up towards applying a treatment. We looked at fear conditioning. There's a poster here by Sarah, which I'll go through briefly. And we've been looking at, say, looming stimuli, whether these heart signals matter when you're trying to apply the brakes when you're driving, for example, and something jumps out at you. Now we've been looking at patient populations. It shows the results from a pilot experiment on fear conditioning. We had 3 groups of people, some of whom saw spiders presented on a computer at cardiac systole. Others saw the spider presented at cardiac diastole, and the control group saw spiders presented for longer over both phases of the heart. So it's a pilot study. The pilot study indicated that those people who stood the course of the treatment and saw the spider at cardiac systole did better. A larger version of this experiment hasn't shown as clear-cut an effect, and there is a modulation again by whether or not an individual is good at the heartbeat detection task. With the fear conditioning experiments presented by Sarah yesterday, we presented stimuli with shocks at cardiac systole or at cardiac diastole and compared them to processing of safe stimuli that were never paired with shocks, again at systole and diastole. What we found was that when people began learning this task, we measured skin conductance as an index of threat processing. Those stimuli that were presented at cardiac systole generated greater skin conductance responses, which mean that they were intrinsically more threatening before the learning had really kicked in. As people carried on with the experiment and learnt to discriminate between the safe and the threatening stimuli, the effect was obliterated still at systole and really only manifest at cardiac diastole. So it seems that systole has an intrinsic kind of threatening aspect during this experiment anyway. And when we looked at who showed the effect most, it was those people with high trait anxiety. This is again the early part of the experiment where systole enhances the threat value of stimuli in people with high trait anxiety. People did learn which stimuli were threatening and safe when you asked them. This is shock expectancy. But still, they didn't really like the stimuli presented at systole, even though they knew it was safe. This is the safe stimulus, CS minus at systole. The pleasantness rating is much lower than the CS minus at diastole. The experiment went on to extinguish people's learnt conditioning. What we did was, for half the stimuli presented at systole, we switched contingencies. Half the people had switched contingencies and half had the same contingencies. And actually what this shows was that not only was this intrinsic effect of systole present to make the stimuli more threatening, but there's also a context effect, so that if you switch contingencies, you learn to extinguish the stimuli faster than if you stayed in the same contingencies. And again, the effect of systole after extinction still made the CS minus unpleasant. So the reinstatement, similar kind of thing. Skin conductance is greater at systole after reinstating the learnt fear. And again, expressed in people with high trait anxiety. So the main findings were that stimuli at systole are inherently more aversive. The body acts as a context as well. So we saw that during the extinction phase. When you get a switch between systole and diastole of a stimulus, you extinguish quicker, you eliminate the conditioned memory. And then trait anxiety augmented the heightened fear at systole. Okay, so other examples of how we've been using this interoceptive effect on fear is to explore processing of looming stimuli. It's supposed to look a bit 3D for you. But we did it with virtual reality. So we had projectile stimuli of different sizes being projected towards subjects in the scanner. If they saw large stimuli coming towards them at cardiac systole, they reacted quicker than if those large stimuli were presented at diastole. You had small and large stimuli. So there's an effect of cardiac signals on reaction time dependent on the salience, the stimulus size, but not on the speed in this case. And then lastly, I wanted to touch on how we've been exploring this heart-brain emotion effect in patients. We took the basic protocol of presenting fear faces at systole and diastole, comparing them to neutral faces at systole and diastole. We also got people to do various tasks and questionnaires. And across different patient groups, I think we have now reached over 300 patients. We look for differences in this heart fear effect. So we sampled people with a variety of different conditions: major depression, bipolar disorder, anxiety, including OCD and PTSD, and mixed anxiety and depression, personality disorder, and psychosis. And really all of them showed this relative enhancement of fear processing at systole compared to neutral faces at systole, except people with psychosis. And I think this is interesting because we're getting lots of differences in the psychotic group that we don't see in these mixed affective groups, and including anxiety, depression, bipolar. So there's something going on within the psychosis group that is uncoupling the interoceptive influence on emotional processes as revealed by this relatively simple interoceptive task. And it's interesting that yesterday I found a paper by Andre Schultz showing that the cardiac effect of that he's been looking at on startle responses isn't there in people with depersonalization disorder. So people that dissociate seem to have problems in this integration of physiology with more cognitive processing of emotion. Excuse me. Sorry, Neil gave me this cough. All right, so the heart contributes to effective processing. But it does so in an interesting way, because it contributes differentially. It means we're not constructing necessarily a non-specific arousal to enhance the processing of all emotions when we look at the systolic effects, because we're getting a differential response. So there's an intrinsic negative threat aspect to these heart signals. So fear experience is enhanced, pain suppressed at systole. And that difference between the threat of something averse happening and the actual occurrence of pain is quite interesting. It means that if your heart is beating strong and fast, you're not going to feel pain so much. You can run away from the bear quicker, but you're still alert to other threats that may leap out at you. Yeah, we're saying that fear detection is enhanced at systole. We've got particular brain regions, including amygdala and insula, alongside dorsal brainstem regions implicated in this integration of interoceptive effects with emotion. Not everyone shows these effects. I've tried to illustrate individual differences in physiology, anxiety state, salience of stimuli, and the looming stimuli. There are other things we've investigated in other contexts that I haven't gone on to. Showing that heart signals affect fear learning and unlearning, so there's an enhancing, generalizing threat in anxious people. It possibly facilitates threat extinction. There's a context effect, so body state is there as a context as well as this intrinsic threat value of systole. And we're getting differences in magnitude across patient groups, with the psychosis group being distinctly different from other patient groups. We've looked at this effect in a variety of other contexts. We've looked at interoception, the heart timing effect as a function of impulsivity. If you're a more impulsive person, then being in a state of higher arousal or seeing stop signals at cardiac systole is going to help you control your behavior. It's a paper hopefully coming out soon from Manos Tsakaris and Ruben Azevedo showing effects of cardiac timing, this cardiac signal modulating performance on tests of implicit racial bias. It's quite interesting. I've not touched on interoceptive predictive coding, selfhood and empathy aspects of interoception. And we have looked at neurotransmitters and pharmacological manipulations, both at the periphery and centrally of these effects. So I'd like to acknowledge Sarah Garfinkel for leading most of this research and other members of the team. Neil Harrison's here. I'm funded mainly by the European Research Council, funding from Dr. Mortimer and Teresa Sackler Foundation. So thank you all.